In this presentation, we'll see how to create a simple block design in Vivado with Microblaze as a microcontroller, and then program the Microblaze using C in Xilinx SDK. So first of all, we'll create a project. So hit next. Now give your project a name. So let's give it a name, Microblaze MCU. Then create project subdirectory, so it should be checked. Then hit next. Then do not specify sources at this time, so let us create an RTL project. And then we don't have to add any sources right now, so hit next. Yeah, hit next again. So constraints also we'll add it later. So I have the Xilinx USB 104A7 board. So here is that board. So USB 104A7, I'll select my board. So in case you are using any other board like RT, you will have to select that. Hit next. So then click on finish. Now a project has been created. Now we'll create a block design. So click on create block design in the IP integrator. So give it a name and it should be local to the project. Click on OK. Now that we have got the empty space to create our block diagram, now we'll close this catalog and project summary so that we'll have some more space. So first of all, we'll add the Microblaze itself. So click on add IP, then type Microblaze here. So it'll add the IP. Yeah. So once we got this, we'll run block automation. So this block automation is a very useful tool to easily create block designs. So click on it. Then there are several preset options available. So since we are going to use it as a microcontroller, we'll select this. In case you are going to use some RTOS or something else, you can select real time or some other application. So in this case, you'll select microcontroller. Then local memory will have the maximum possible 128 KB, and then leave other options as it is, and then clock will enable it as 100 megahertz clock, as a new clocking wizard will be created with this block automation. So click on OK. Now we will see that some other peripherals will also be added into the block design with Microblaze. It will take some time to load the components. You can see that in the tickle console what and all commands are being run. Yeah, so now we have the other peripherals added here. Now what you can do is you can click on the regenerate layout. Then you will see that the layout has been regenerated. So next what you can do is you can run connection automation. So in the clock wizard you have few options, but then right now we won't do it because there are some problems in the board. Problems in the sense there are some limitations, we have to do something extra. So what we'll do, we'll go to window and select board. So once we have since we have selected the board part, we'll get some board peripherals also. We'll add the system clock first. We'll just drag it and then we'll place it on this, and you'll see that the system clock has been configured with the clocking wizard. So double click on it. and you'll see that the clock in one is the system clock. And then the clocking options, we have few options here, so leave it as it is. In the output clock we have 100 megahertz one output clock, duty cycle is 50%. And then reset type, it is active high right now. So few boards like RT have reset, like a dedicated reset button on the board itself, but in USB 104A7 we don't have that facility. So in this board, so what we'll have to do is these are the only IOs, GPIOs available, so there is no dedicated reset. We have only two push buttons which are active high. So active high in the sense they'll be active only when they are high, so they are pulled down, they are pulled down basically. So in the normal condition we have 4 LEDs. So what we'll do, we will create a simple NOT gate. That's because in the processor reset system you will see that I'll zoom in. So in the processor, so you'll see that the external reset in is active low, whereas in the clocking wizard we can keep this as active low also, but then the push button available on board is active high. So what we'll have to do is we'll have to create a NOT gate, and then we'll connect the push button directly to the reset, and then we'll give a NOT gate, and then we'll give it to the external reset in. So in this, if you double click the processor reset system, you will see that this external reset logic level we can't change it. So that's the problem here. So now what we'll do, but yeah, this is a very simple issue, we can solve it very easily. We'll go to sources, and then we'll add one new source, add or create design sources next. So we'll create file, so Verilog NOT gate, we'll give it a name NOT gate, okay, and then finish. So one input, and then no, it's not a bus, so one input and then one output. Yeah, that's all. So it will create the Verilog file. So once it is updated, we have to write the RTL definition for it. So now we have the NOT gate. So it's going to be very simple: input A, some variable, comma, and then output Y. That's all. Then assign Y equal to NOT of A. That's all. So this is the RTL code for a NOT gate. So we have input, one input and one output. The output is the complement of the input. That's all. So now what we'll do, before connecting the reset, we'll have to pull this NOT gate module into the block design, and you will see that the module has been added. Now what we'll do, we'll connect the output of the NOT gate to this external reset, and then we'll click on this reset, and then we'll make it external. Yeah, so this has been made external now. Now we'll connect this to this reset. So this reset is active high, as in the schematic. We'll connect one button, this button 0, to the reset, to this reset, clocking wizard reset, and then we'll give it to a NOT gate, and then we'll make it as active low, and then we'll give it to external reset in. Now what we have to do, we'll have to create a constraints file now. So add or create constraints, add files. So I'll go to the, so USB 104A7, yeah, this is the file. So now we have the constraints file here. This is the master constraints file. So what we'll have to do is we have the reset here, right? So we'll just rename it. We'll rename it as reset. So this reset has to be connected to this button via the constraints file. In the constraints file we have this button here. So we'll uncomment this, and then instead of button 0 we'll have to give the reset. Yeah, so that's it. So for now this is done. The reset, same name should be given. So reset is connected to the button now, the constraints file. So next, once this is done, we'll have to add the GPIOs. So click on this add IP, then AXI GPIO. So let's have this for the input, one input, and then for demo purposes I'll show one output also. So again click on add IP, AXI GPIO. So we have two AXI GPIO. So why should we have this? So AXI is basically a protocol. So I think it was developed by ARM. So this AXI is used to interface with the Microblaze, that is to interface the outside peripherals hardware with the Microblaze via this AXI interconnect. So these once we run the connection automation, you will notice that the AXI GPIOs, these two AXI GPIO IPs will be connected to the AXI interconnect, and then we'll connect the external hardware to this AXI GPIO. So we'll run connection automation. So we'll check this, but whereas in GPIOs it has some default things. So for GPIO 0 we'll have it as input, so this will put it as custom, so we don't want this. In GPIO 1 let it be the LEDs, so we'll have this as it is, because you know that there are 2 push buttons and 4 LEDs in the USB 104A7. So we'll have 4 LEDs connected to one GPIO as output, and then let this be input. So we'll leave it as custom because already we have used one push button for the reset, for the processor system reset. So click on OK. As any microcontroller has some reset button to reset the program running, that is why we need to have the reset facility. So now we have the connections, the AXI connections, they are done. We'll regenerate the layout. Yeah, so once we are done with this, we have the AXI GPIOs. Now what we have to do is double click on this. So, and you will see that the GPIO is custom board interface. Then in the IP configuration, click all inputs, and the bus width will be 1 because we have only one push button, so the GPIO width will be 1, and then all our inputs. Click on OK. So once you do that, you can see some arrow coming here. Click on it and you will see the one input. So you have it here. Now you would right click on it and make it external, so that the external push button can be connected to that. So the inputs will be on the left side and the outputs will be on the right side. So we have this here. Now we'll change it to GPIO IP, indicating that it's an input. So yeah, it's done. So the 0 0 indicates that it's just one bit, one width long. So again we'll regenerate the layout. So once we regenerate the layout, it's done. So next what we'll have to do is I'll show you the block diagram in the full size. So these are we have the clocking wizard, and the system clock is connected to the clocking wizard, and then the clock out is connected to these peripherals in our system, and then we have the reset here. Since the reset is active high for clocking wizard, whereas it's active low for the processor system reset, we have added a NOT gate, a module via the RTL design, simple NOT gate, and then we have the one GPIO input which is 1 bit wide, and then we have the AXI interrupt controller, and then the Microblaze debug module, and then the local memory. All this was added automatically through connection automation via the Microblaze. And then we have the AXI interconnect, which interfaces the AXI GPIOs to the Microblaze. And then we have 4 LED buttons. So one more thing that we would like to add is the UART. That is because to debug things and to print to the terminal, since we don't have any LCD displays on the board, so to print it to the terminal we'll have to add the UART. So UART light, so AXI UART light, so we'll add this. So we'll have the click on run connection automation, then click on all automation. So you'll see that this is there, and UART will be connected to the USB UART in the board itself. So click on OK. So this is done now. The one which I was talking about is, once you click on board, you'll notice that the USB UART. So this USB UART will be automatically connected to the AXI UART light. So this is done, and then the 4 LEDs have been connected. 2 push buttons in custom way we have connected, one to the reset and then one as the input, because every microcontroller system should have MCU should have one reset button. So we have made it custom, and then the system clock is connected to the clocking wizard, 100 megahertz clock output. So that's it. Now click on regenerate layout. So this is our final Microblaze design. So we have system clock, reset, and then one GPIO input to the AXI GPIO, and then USB UART, and then we have 4 LEDs. So that's it. Now what we can do is we can go to sources, right click on this design. As you can see right now it is showing the NOT gate as the top module, whereas once we create the HDL wrapper, this NOT gate will get into this design, because this NOT gate is just a part of this design. So this is the top module. So create HDL wrapper. So let Vivado manage. So this, select this manage wrapper and auto update. Click on OK. Generate the HDL wrapper. So you'll notice that this NOT gate will vanish and it will get into the design, because this is a part of the block design that we created. Updating. So as you can see, this NOT gate went inside this. And then one more thing that we have to do is this GPIOs, we'll have to add these to the constraints file, because even though we have made it external, we should make this visible to the external hardware. So go to the constraints file, and then the system clock should be connected to this 100 megahertz clock. So this should be system clock, sys clock. So just make sure it's right. So this one is sys clock. Okay, and then we have the reset here. Reset, I think we already did it. And then we have GPIO input, that will be the second push button. So the LEDs and USB UART we need to configure here. Even the clock we need not mention it here. Only the custom GPIOs we'll have to mention it here. That is why, because the block diagram itself will manage all these in a constraints file that it will create. So we don't have to mention all these. So this is our final diagram now, final block design. So once you are done with all these, you can click on generate bitstream. So you'll have to first synthesize, and then you need to run implementation. So click on yes. So number of jobs is 8, and click on OK. We'll start synthesizing. So as you can see, the design runs has started. So once you click on this, you'll notice that all the blocks are being synthesized now. So all these blocks, clock wizard, and then the RAM, then the Microblaze AXI interconnect, and all those things will be synthesized first, and then once these are synthesized, the actual the final HDL wrapper will run synthesis and implementation. So the bitstream generation has been completed. So I'll click on view reports. So okay, and then as you can see, the design runs, there have been all the design runs that have run here. All these blocks and modules that we added in the block design, they have all been synthesized, and the report shows a number of LUTs and flip-flops used, and finally we have 1710 LUTs and then 1466 flip-flops used in our final design. Go to file, then export. We need to export this hardware in order to launch the Xilinx SDK. So once I'll show the complete block diagram. So this is the block diagram. Right click. No. Yeah. So this is the final block diagram that we have done here. So yes. So once this is done, we'll have to click on export hardware. So in this option, click enable the include bitstream and then export it to the local to project option. So once you click on OK, the export process will take place. Then once you are done with that, what you'll have to do is this exported design will be done to launch the SDK. So once you have exported the design, you can launch SDK, and then the SDK will take the file exported through this hardware. So launch SDK. So export location should be the same local to project. Then click on OK. Wait for some time and it will launch the Xilinx SDK. So you should launch the SDK only after exporting the design. Run the export option. So the SDK will load now. So once the SDK has been launched, it will launch the hardware. So it will import the hardware specification. So that the one which we exported from the Vivado. So it will import it. So as you can see, this is the imported this is the imported design from the Vivado. So we have all these IP blocks present, the NOT kit which we created, the clock wizard, the AXI GPIO, the Microblaze itself, all those things, and you can access the registers also. Now we'll go to file, new application project. So give this project a name. So we'll give the same name, Microblaze MCU, and then the default location will be the same thing. Then C, you click on next. So the BSP will be the Microblaze MCU itself, which we exported from there, and then the language will be C. The processor should be Microblaze 0, then design 1 wrapper hardware platform 0. OS is standalone, we are not using any RTOS or Linux. Then click on next, and then let us just run a hello world to verify our design, the design which we created. So click on finish. So now the application project has been created. Go to source, and in source click on hello world.c. So you will see a simple hello world program. So this is very simple. We just include a Xilinx printf library, and then this print will consume very low memory, so we are using this, but this can print only strings, constant strings. So printing hello world. Now what I'll do, I'll show you how all this works. So first of all, we have this board here, the board is running, and then there is an out of box demo running here. So now what I'll do, I'll open the SDK terminal. So in the terminal, I'll add a serial port, So port com 9 9600, click on OK. Now open the camera again. Now in the out of box demo, once I click on this button, you will see that the button pressed notification button press detected. So this is the out of box demo. This will change, the LED will change direction, but you can see that this is the demo, this is the FPGA is programmed with the demo program right now, the button press, not this program. So you will see that this is running now. Now what we will do, we will clear this, and then we have to program the FPGA. So go to Xilinx, and then you have the option called program FPGA, click on it. Now this we have to program it with the design one wrapper.bit. So as you know that the design one wrapper is the top level module of this block design. So of this block design we have the design one wrapper. So this bitstream we need to program into the FPGA. So this is the bitstream that we have selected for this, and then the processor is Microblaze. Now click on program. So once you program the FPGA, we will see we can notice that the blinking LED demo program will stop. So click on program, I'll show you. So this will start programming, initializing stream. So this program will stop running once the FPGA is programmed. It's creating bitstream now. So it's configuring now, it's configuring the FPGA with bitstream. As soon as it's done, you'll see that all this now it shows FPGA configured successfully with the bitstream that we had done. And you also notice that this blinky program has gone, because now the FPGA is programmed with the bitstream that we designed. So now what we'll do, we'll go to the SDK terminal. Now it's already connected to the COM 9600 baud rate, so it's written here. Now we'll run this program. And we'll see if we are getting the output. Now click on this run button, and now you'll see that there is an option, there are so many options. There's an option called launch on hardware. Now click on it. So once you launch on hardware, now once you see that once this program has been launched, it will program the MCU that we designed, the microcontroller, the Microblaze, and then it will print the hello world into this terminal. So click on OK. Yeah, so now as you can see, the hello world has been printed. So if you run the program again, the same hello world will get printed again. As you can see, launching CDB gigabytes. Yeah. So this is how the Xilinx SDK works. So the FPGA has been programmed using the bitstream that we generated from this block design, and then we have created a simple application project in the Xilinx SDK and a simple hello world program through the UART. So this is because we have the UART Lite AXI. So this peripheral is responsible for the USB UART. So using this only, it prints into the terminal. So in the next video, since this video is getting too long, I'll create another video. So the next video we'll see how we can interface the GPIOs in the board, and to create a simple LED and push button based program and use the SDK. So that's it for this video. Thanks for watching.